guys, imagine that this is your metal itself, right? Okay, so this is your metal itself. And now what's going to happen is the lightning is going to deposit negative charges on it. All right, so the lightning is coming in, and notice that the negative charges are being deposited. So these negative charges will reside right at the surface. So negative charges will get distributed onto the surface that you're looking at. So what is the net charge on the inside? So the thing to do is you need to just take your Gaussian surface, and then you will have to place your Gaussian surface right where this surface is, like right inside of the surface. That's what I'm doing. All right, so the green is going to be our Gaussian surface. All right, this is your Gaussian. What is the net charge on the inside? So the net charge is going to be on the outside. So the outside charge is going to be negative. All right, so the charge is going to be outside is going to be negative charge. So net charge, excess charge is going to be outside. What is the net charge on the inside, if that's the case? All right, so the inside charge is going to be 0. Net charge on the inside is going to be 0. If the net charge on the inside is 0, what happens? If this is 0, area is not 0, which means that the electric field on the inside is going to be 0. All right, so strength of the electric field intercepted by this area, this is your total area. All right, so solve for the strength of the electric field on the inside. This is the net charge on the inside. And the net charge on the inside is 0. If the net charge on the inside is 0, the electric field on the inside is going to be 0. All right, so which means that the electric field on the inside is going to be 0. Electric field is what drives the charges across a region. Electric field is what drives the charges across your body. If the electric field on the inside is 0, you're perfectly safe. You're not going to get shocked. You can touch the inside of the metal. There's no electric field on the inside. You can touch it with both hands. You can put your face next to it. It makes no difference. You're not going to get shocked because there's no electric field on the inside. All right, so the like charges, when deposited onto a metal surface, a metal enclosure, in general, they will be repelled to the surface, and then they will get repelled away as far away from each other as possible. The furthest that they could get without leaving the structures and the surface of that structure. And on the inside of the enclosure, you're going to be perfectly safe because the net charge on the inside is going to be 0, which means that there's no electric field on the inside, forcing the charges to go through your body. That's the reason why you would be safe inside a metallic enclosure, otherwise known as a Faraday cage. Examples of Faraday cage: you got your car, obviously you got an airplane, and every single sensitive electronics is going to be enclosed inside a metallic Faraday cage, like your computer is going to be housed inside on purpose. All right, so here's a car. It's getting struck by artificial lightning. You got a spark generator there. Notice that the tires don't help. It's going to go right through the tire. So as long as you remain on the inside, you're going to be perfectly safe.
If you can't do that, you should get into a metal car.
The car's metal body discharges the current away from the driver and true or false? You can be electrocuted by lightning in your car.
True or false?
False.
It's going to be 100% false. All right. The answer is false. You cannot be electrocuted by lightning in your car. It's out of the question. Conditionally. Provided that you got your windows up.
The answer is true.
So answer is true evidence. So that got my attention. According to physics, you're perfectly safe. And they're claiming that, nope, you can't be struck by lightning inside a car. Of course, as soon as I was watching this, I got all excited because I want to see the evidence of physics being wrong. Okay, that's the sort of stuff that gets you excited if you're a physicist, which means that there's something wrong with the physics, which means that you can do research on it. So I'm looking forward to actually seeing the evidence of someone getting fried.
You're about to see actual video of what it would look and feel like if it happened to you.
All right, so the car gets struck. The guy is screaming, but he seems to be okay.
Oh my God!
The windshield wipers are working, which means that the electrical system wiring is open.
The car is just struck.
The engine is still running, so the engine is okay.
Lightning! Oh my God!
Oh, I'm looking at the clock. The electronics is okay. So the question is, what the hell, guys? I mean, everything is fine exactly the way the physics predicted it. Did he get shocked? Maybe emotionally, but not electrically.
A man from Colorado was lucky not to be electrocuted.
Are you kidding? As far as physics is concerned, he's not supposed to get electrocuted. It has nothing to do with law. He's inside.
The outer surface of his car.
This guy is a storm chaser. So his camera was running.
The hit, blowing out his tire. As the
tires didn't help.
lightning sliced through his car and into the ground.
What happened was it hit the radio antenna. It used
Antenna got vaporized.
to be right here. The antenna going up about that high.
If you find yourself driving...
And I love their conclusion. All right, guys, this is the sort of stuff that you could write for the Science Channel,
through a lightning storm.
Channel, or History Channel today. If you're an English major, and if you have zero understanding of physics.
Pull over and keep your hands on your lap. Don't touch metal like the steering wheel or the radio.
Was he touching metal like the steering wheel when he was driving? Yeah, he was, right? Did he get shocked? No. Pulling over?
That way.
Lightning storm. If you pull over or if you stop driving in the middle of a lightning storm, if I'm behind you guys, if the traffic comes to a stop or slow down, I will come after you with a baseball bat. All right, just keep driving. Being inside a car is just about to be the safest place where you could be during a lightning
You'll
storm.
survive this.
You will survive that 100% of the time. If you're in that.
The monster created by a man they called Mad is turned loose to strike terror into the hearts of men. Austin Richards is a self-described mad scientist. But tonight, he's going to play both Dr. Frankenstein and the monster at the same time. He plans to zap himself with 2 million volts of electricity, protected only by a homemade metal suit.
I've really been obsessed with the idea of being a mad scientist. The mad scientist knows exactly what he's doing, but at the same time, there's sort of an element of unpredictability to what he's doing. Sometimes it gets out of hand.
Austin's interest in current events began when he was 14 years old. For a Halloween show, he built what's known as a Tesla coil, a machine that shoots fiery bolts of electricity through the air.
And that first Tesla coil made sparks that were about 12 inches long.
Tonight, Austin is unveiling his latest creation, 2 giant Tesla coils that can fire 2 million volts over 20 feet. But he isn't satisfied with just watching this dangerous light show. He wants to be part of it. Austin knows he could never survive a direct hit from the giant coils without some sort of protection. So he designed a special suit made of metal that would transform him into a human lightning rod. The idea for the suit first came to him at a restaurant, and he quickly scribbled his original design on a napkin. Eager to bring his creation to life, he went shopping for parts at the local hardware store.
So I started selecting bits and pieces of heating duct and dryer duct, actually trying them on my body, slipping them on my arms and legs, and I got some interesting comments from some of the people that work there.
That makeshift suit has now evolved into this, makeshift suit. And though he may not make any best-dressed lists, Austin hopes his suit will protect him from a 2 million volt direct hit.
What we're going to try is something that's never been tried before, which is to create almost, in a sense, double jeopardy, having 2 Tesla coils, suffusing a whole area with electricity, and I'm going to put myself right in the middle of it.
Austin has invited a select group of guests to witness this terrifying experiment. Are they going to see an electrifying performance or an electrocution? Austin begins by displaying the awesome power of the giant Tesla coils. He holds up a block of wood. It bursts into flames, but he's shielded by his protective glove. So far, so good. Next, Austin ups the stakes by raising up a solid steel wrench. It's bombarded by a barrage of bolts, but he's still okay. Now he's going to step right into this electrical storm and subject himself to 2 million volts of white-hot lightning. This scientist must be mad. If Austin's homemade suit should fail, he could be fried to a crisp.
If I haven't done my safety check properly, I could die.
He cautiously moves into position. The coils surge to life. Millions of volts of raw power pound his body. The shocked onlookers can't believe what they're seeing. It only takes 100 volts to kill someone. So how could Austin survive 2 million? Incredibly, he's done it. Austin's electrifying experiment is a success.
I was really hoping that it was going to work, in the sense that I was really hoping I wasn't going to get killed or injured. And I remember feeling a really deep sense of relief when the arcs began hitting and I didn't feel a thing.
Beaming with success, Austin lights a cigar to celebrate. His crazy homemade suit actually works. Maybe this mad scientist isn't so
If you knew that you were about to be struck up, and if you were to jump, would that prevent you from getting struck?
mad after all.
No, right? So which means that you don't need to be grounded, which means that you don't need to be touching the ground. So the excess charge is going to reside outside the metal container. Electric field inside the conductor is going to be 0, so you got this conducting material. So within the enclosure, the electric field is 0. So what that means is that any conductor is going to shield any charge within it from electric field created outside the conductor. What that means is if you have any sort of sensitive electronics that needs to be protected from any accidental sparks from outside so that it doesn't get fried, you have to place it inside a metallic enclosure. Hence the reason why all the sensitive electronics are usually housed inside metallic enclosures.
When a thunderstorm forms, people's lives can be at risk.
We tell people when thunder roars, go indoors. What we mean is seek a safer shelter.
If you're ever caught out in a thunderstorm, one of the safest places to be is in a closed vehicle.
Many people believe the rubber tires on a car will keep them safe, but that's not true. It's the car's metal body that provides protection. As this high-voltage experiment will demonstrate. A Tesla coil is the lightning simulator, an electrical transformer that discharges 3/4 of a million volts of electricity, more than enough to kill. Dr. Lisa Lazarek is an electrical engineer who's willing to sit in a car underneath the coil to prove that the metal body will protect her.
The electrical charge striking this car is going to conduct around the outside surface of the enclosed body, so I should be fine as long as I don't touch the metal of the car. But it's one thing to talk about the theory, and it's another thing to put it into practice. So I guess I'm ready.
The electrical charge flows around the metal body of the car and discharges harmlessly to the ground.
I'm fine. The theory has worked as expected. My feet are slightly tingling, and because I was nervous, my hands are still clamped together. But other than that, I'm fine.
All right, so what's wrong with the explanation that you provided? All right, she has a PhD in electrical engineering. Engineering is applied physics.
You could be touching a metal and it still wouldn't.
All right, this is one of the things that I really hate about the education system. This is when you learn these facts. Right after this level, everything gets mathematical. Notice that you don't get a chance to catch up after this. She's got a PhD in electrical engineering. She's an expert in this, and she's afraid to touch the inside of the metal because she doesn't understand the concept. All right, you can touch all the metal on the inside. You're 100% safe. Forget about touching the metal on the inside. I can also tell you that you can touch the metal on the outside. You're still going to be 100% safe. So the question, now you get it. You get the fact that you can touch the metal on the inside, but how can you touch the metal on the outside while you're sitting on the inside, and why is it that you're not getting electrocuted? Well, that's the next lecture, obviously. All right, so this is what I'm trying to prevent from happening. You can get a PhD even if you don't understand physics. You can even get a PhD in freaking physics without understanding what the hell is going on, guys. I know what I'm talking about because I worked at Fermi Lab. And then you get these guys from Harvard, and as soon as they start to discuss physics, you go, wow, these guys get to math, but do they really understand what they're
conduct around the outside surface of the enclosed body, so I should be fine as long as I don't touch the metal of the car.
You can touch the metal of the car, you're still fine because you're inside the metallic enclosure. The strength of the electric field on the inside is zero, and electric field is what drives the charges across your body. If there's no electric field, there's no chance that you're gonna get yourself electrocuted. Okay, next question. Once the charge is outside, the lightning is going to strike, and then it's going to deposit light charges onto the metal surface, right? What is the component of the electric field which is going to be parallel to the surface? Okay, so these are the sort of questions that you will tackle on the conceptual portion of the task. As soon as it becomes a static distribution, what is the strength of the electric field on the surface? What is the strength of the electric field which is parallel to the surface? What's the value of the strength of the electric field which is parallel to the surface?
0.
None. Okay, who said 0? Okay, in justify. Strength of the electric field parallel to the surface is going to be 0 because
they're going to cancel each other out.
Right, if it's a static distribution, guys, which means that charges are not moving, right? Along the surface, charges stop moving. The reason why the charges stop moving is because the net force acting on each and every single charge is going to be 0, which means that the component of the electric field, which is parallel to the surface, is going to be 0. That's what it means on each and every single charge. Or else you would have currents on the surface, on the surface. All right, Ian, give yourself 10 points for that one. So the only surviving component on the surface is going to be the component which is perpendicular to the surface. All right, and so which means that the only component which is going to survive is going to be the component right on the surface. Notice that the charges will not be uniformly distributed if the surface is not smooth. Notice that the charge concentration is going to be much higher for line sharp edges and the pointy corners. Is that making sense? So the shape is going to matter. Sharper the edges are, the higher the charge concentration is, which means the charge density is going to be large. The strength of the electric field is going to be large at the same time. All right, so the charges will be distributed along that surface. You're going to end up getting a static charge distribution, which means that the net force acting on the charges will be 0, which means that the component of the electric field, which is parallel to the surface, is going to be 0.
Basically, you have a thundercloud with a positive charge sitting in the upper region, negative charge at lower altitude in the central region of the cloud. And the separation of those two charges creates a potential, a voltage of several hundred million volts.
These oppositely charged regions of the cloud are highly unstable and very attracted to each other. A lightning discharge is in some ways like a gigantic version of a common static electrical shock. When these sparks occur within a cloud, they are called intercloud lightning. When a negative charge in one cloud flows to the positive charge in another, the result is cloud-to-cloud discharge. Sometimes the negative charge in the ground, especially in tall structures, will jump directly to the positive charge in the top of the cloud. But the deadliest discharges are cloud-to-ground strikes. The Earth has a slightly negative charge, but the powerful negative charges at the base of the storm clouds repel the negative charge, causing the ground to become positive. When the attraction between these charges becomes strong enough, there is a spark.
All right, guys, we'll take a break.